Okay, so thank you for waiting. So this lecture is an introduction to some basic principles in thermodynamics. It's meant to be fun. Normally I lecture on the board. This is much more interactive. You're all holding the text for today, which is Statistical Physics for Babies by Chris Ferry. And then two demos, an instant hot pack and an instant cold pack that we'll use. So wait until I tell you and we'll all pop those hot and cold packs in the context. So I want to start by reading from the text. So I'll just read this to you and you can read along with me. Okay. This is a great book. All right. So this is a ball. This ball is on the left. Now it's on the move. So we gave it some thermal energy. So it's moving. Okay, now it's on the right. So it moved over here. Okay, so now we have 6 balls. All right, so we have 6 balls here in a space that's divided by a dashed line in 2. So it's clear that the balls can go left and they can go right. And we gave them some thermal energy, so now they're on the move. So they're bouncing around. So sometimes you might find more on the left. Right? And sometimes you might find more on the right. But you'll almost never find them all on one side. Right, that would be pretty surprising. It doesn't seem impossible, but it'd be surprising if things are random. We all agree with that? Okay. So we normally find them like this, right? It looks pretty evenly distributed around the space. Okay. So now that was the first 10 pages. Now I'm gonna lecture a little bit on that. So let me give you a slightly more scientific explanation of what we just read. Oh, chalk was right there. Okay, so just for today, when I have slides, I get squished over to the right-hand side board. Normally I lecture on the board right in the middle. So I apologize today. These lecture notes are going to be posted. They are already posted to Stellar if you have trouble seeing. So what we're going to do is we're going to draw a cartoon of non-interacting gas molecules in a box. So we're going to start like this. We're going to have a box. And the box has a divider. On the right-hand side is vacuum. And the left-hand side are 6 gas molecules. And I'm going to give them some thermal energy. So they have a finite temperature. They're kind of zooming around. And they don't interact with each other. They just bounce off the walls. So the first thing we're going to do is we're going to remove the partition. So I'm going to draw a dashed line where the partition was. And at the instant we remove the partition, they're still over here on this side bouncing around. So remove partition. Right, so we remove the partition. OK, now what's going to happen? Yeah. OK, so this is what's going to happen. So what I'm going to say is the next step is we just wait. We don't do anything. We just wait. And we probably don't have to wait very long, right? We don't have to wait very long before the gas molecules are randomly distributed around the space, zooming this way and that. So, right, OK. So you all buy this. So let me tell you what happened in thermodynamics speak. OK, so this is a key word in thermodynamics. This happens spontaneously. The volume of the system here, at this moment, when I removed the partition, was small. And spontaneously, without us having to do anything, it got bigger. So all we had to do was wait. It was a spontaneous process. So you could say the volume spontaneously adjusted within the limits that we imposed, that is, the box is still there, to increase the amount of disorder in the system. OK, so now I'll ask you a question. Why?
Probability is higher, the number of combinations there's a greater number of them that the atoms are more spread out.
Okay, that's exactly where we're heading. Let me rephrase that. That was the correct answer. Because the more disordered state is more likely. So we're using a frequentist definition of statistical likelihood. All right, back to the book. Okay. So now he does a better job explaining this than I did. So let's go back to the book. All right, so now we're on page 11 where the balls now have different colors. Okay, so now we have 6 balls. Now each ball is a different color. All right, so there's only one way you can have all the balls on one side. That way is have all the balls on one side. What if we want to put 5 balls on the left and 1 ball on the right? How many different ways can we do that? 6 different ways, right? The ball on the right can be the red, yellow, blue, orange, green, or purple ball. So there are 6 ways to do that. Now, if you started counting up the different ways to have 2 balls on the right and 3 and 4 balls on the left, you would find there are 15 different ways to do that. But what was the most likely situation? 3 and 3, right? It was sort of even. So if you count up all the different ways you can have 3 balls on the left and 3 balls on the right, you'll find that there are 20 ways. So it was 1, 6, 15, 20. So that seems too simple, right? But that's the answer. The reason why this is the expectation, this is our expectation from everyday life, is because it's more likely. There are more different combinations that look like this than any other type of state. And in this case, this has is one combination like this, and 20 combinations like this. So you would say there's something like a 1 in 20, roughly 5% chance of finding all the balls on the left. That doesn't sound that small, right? You take odds on that. But when you start doing this calculation for a mole of atoms or a mole of molecules, you'll find that the likelihood is geometrically small, meaning it's never going to happen. So we, later on in the course, much later, we're going to come back to these concepts and do calculation with something like, what is the likelihood of finding all the air in this room suddenly over here? Right? None of us would be very happy about that. Fortunately, the likelihood is so small you'd have to wait many, 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 many ages of many universes long, and you still probably would never see it happen. OK. So we're OK with that. So physicists, but I should say scientists, because this book was written by physicists, so there's an implicit bias in here. Physicists call the number of different combinations entropy. So that's what entropy is. So a state with a low number of combinations is a low entropy state. Like a state with all the balls on the left is a low entropy state. A state with a high number of combinations is a higher entropy state. OK. So even if the balls all start on one side, as in my example, they're going to end up here because this is more likely. Right? It's an increase in entropy. So the second law of thermodynamics says that things move from low entropy to high entropy. We'll rephrase that later on in a couple of weeks, right? Be a little more technical about it. But that is one form of the second law, that entropy always increases in the universe, never decreases. So that explains why we see these more likely scenarios. In order, you can, if you like, push all the molecules back into the left. But the key word there was push. Right? To do that would take some work. So you can do work on a system and decrease its entropy. Right? You can clean your room. Right? So you can decrease the entropy of a finite system. But in so doing, you're still increasing the entropy of the universe. You're just shifting it around. OK. So things naturally go from organized to messy, just like my kids' rooms. And now you know statistical physics. OK, so do you feel like you know statistical physics? I love this book. Now we're going to fill in some of these concepts on the board. Any questions on the reading? It's yours now. So if anyone didn't get, I think I owe, how many people did not get a copy? 1, 2, 3. Thomas? 4. Anyone else? OK. All right, so we'll get more copies for you. So now we're going to talk about solutions. OK. So yes, Topsy.
What did you mean when you said the overall decrease and
So we'll cover this in a couple of weeks, but the quick answer is that the entropy of a system left alone never decreases. It either stays the same or increases. But if a system is not left alone, if it actually can interact with its surroundings, entropy is something that can be exchanged. So I can actually, if I were a system, I could lower my entropy by giving some to you. Or you could decrease my entropy by taking some. That's
so when you, for example, clean your room, where would that messiness?
when you what?
When you clean your room, where would
The work you're doing generates heat. You cool off, that generates entropy. The most famous example of this is Maxwell's demon. It's a thought experiment. You can fall down quite an internet rabbit hole, or a textbook rabbit hole, reading philosophical style treatises on Maxwell's demon. Maxwell's demon is a little demon that sits in between this box and only lets gas molecules go to the left. And so Maxwell's demon is like a little turnstile for gas molecules. And it's called Maxwell's demon because it was thought of as a thought experiment to disprove the second law. And there have been 100+ years of physics papers showing that for example, there's an information theory approach to Maxwell's demon. That Maxwell's demon has to know that the molecule is approaching. Therefore, it has to receive at least one photon. And you can calculate the physics of the entropy generation of that photon generation and absorption by the demon. So we can make the decision to open the gate. You can't get around the second law. So we'll get there. I don't know if that exactly answered your question, but it was a little, we'll get there again with more time to spare in a couple lectures. So, yeah. Just Google Maxwell's demon. It's kind of fun. OK, so now we're going to talk about solutions. So here comes the first demo. Maybe the last demo. There aren't a lot of demos in this class, but this one is so easy. I did the same demo in 3001. So many of you were in 3001. So I'm sorry, I'm ripping myself off here. But it's topical. So, all right, so there is water. There's water in the dish. You can't see it. So what I'm going to do is I'm going to make a solution. I'm going to mix two substances. One substance is food coloring, which is, of course, also water. But pretend this is like some other substance. It's it's water, like it's some dye molecule solvated, so in solution. And the other substance is water, right? So I'm going to mix them, and you're going to see what happens. OK, so let's see. OK, so while this is going, and you guys know what's going to happen, right? It's sort of, I find, kind of fun and calming to watch it happen. All right, so over here, we're going to talk about solutions. So OK, so we're going to talk about solutions for the case of non-interacting molecules. So I'm going to draw some pictures. All right, so let me see. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. OK, so here's the starting condition. We have some uniform material. It's made of some molecules. I don't know. Right, so here it is. Here's the uniform material in a box. And these are the molecules that make up the material. And its properties are uniform. OK. So now what we're going to do is we're going to label certain molecules. Can you guys see that? Barely. We're labeling certain molecules. So what's one way you could label molecules? Physically, yes.
With its position.
No, what I mean is we're going to make a physical change to the molecule. So it's carrying a label.
Put a tag.
Hmm?
A little fluorescent tag.
Some kind of fluorescent tag. You could make it a different isotope. There's different ways to label, right? Or just as a thought experiment, you just go in and you take, let's say, 5 of these molecules and color them blue to pick a color, right? Which is kind of what we're doing. 1, 2, 3, 4, 5. OK. So I went in and I labeled those molecules. And now I'm going to wait. What do I expect to happen? Yes, please. Yeah, you kind of expect it to even out, right? For the case of non-interacting molecules, initially everything looked even. And then we did something. We made it uneven. And now you kind of expect it to even out. So I'm going to draw again. 15. And you kind of expect the labeled molecules to spread out. Maybe like that, right? OK, they're not all on one side anymore. You get it. I didn't want to spend all day up here drawing circles. It's more convincing if I do like 20 or 30 circles. But I decided to stop at 15 circles. So what's actually happening, right? I mean, you understand that and you believe that. I'm just going to describe that in thermodynamics language. So what happens is that diffusion OK, so the process by which this concentrated area of labeled molecules becomes diffuse is diffusion. And it happens spontaneously, right? I don't have to go over there with my atomic tweezers and move the blue food coloring molecules until they all look even. I think by the end of this course period, it will be uniformly blue. It takes about half an hour or so at the temperature of an overhead projector. OK, so that's the diffusion process. And again, that word spontaneously. It's happening spontaneously. And it's mixing the labeled molecules. So what can you say about the entropy of this situation? Is the entropy from the second frame to the third frame, is it going up or down? It's going up. Something's becoming more disordered. Right, that's true. The entropy is going up. There's more different configurations that look like this, all mixed up, than configurations that look like this, everything on one side. Right, so it's more likely, it's more entropy. All right, so now I'm going to erase this board and redo it for the case of molecules, and now we're going to interact with each other. Yes, please.
Not spontaneously. I thought before when we were talking about the removing the
Yeah.
the spontaneously is indicate instantaneously or without?
No, it doesn't mean
outside-
instantaneously.
without outside.
Exactly, that's right. It does not mean instantaneously. There are many good examples of this, of systems that are out of equilibrium, that are slowly relaxing. If you go to very ancient cathedrals, you'll see that the windows appear to be pooling at the bottom of the window frames. They're slowly, like, flowing. Right? Things seem static. In the case of gas molecules, it'd be about hundreds of nanoseconds in a reasonable space. So the time scales might vary. Yeah. But it's a good question. It doesn't mean instantaneously. It just means without outside influence. Right, thank you. OK, so now let's do the case. My favorite example here is there's something called the tar drop experiment. And this is at a university in Australia where they took some tar and they put it in a vessel. And they poked a hole in the bottom of the vessel. And they put a video camera on it. And it's been running for decades. And I don't remember, but once every 8 or 9 years, you get a drop. And there's a webcam for this thing. You can go and watch it. You know? So spontaneously, it's dripping. But it's pretty slow. OK, so now we're going to do the case of interacting molecules. So the previous example, and the example you're watching over there, there's effectively no interaction between the labeled molecules and between the labeled molecules and the unlabeled molecules. There's not a lot of intermolecular forces in between the blue dye and, let's say, a distant water molecule, or between two distant blue dye molecules. Not a lot of interaction. So what about when there is interaction? Let's do the cartoon case, and then we'll start. This is how we get towards the hot and cold packs. So we have a uniform material. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, so we're starting again with the uniform material. And now I'm going to, let's see, I sort of label some, right? So just as before, I'm going to label some. This time, the ones I'm going to label are all right, I'm going to label them in a way that is sort of more like what you would expect from the equilibrium situation for the non-interacting particles. OK. Label some. OK, so now I've labeled them quasi-randomly. And now I'm going to make a caveat. Label some so that they attract. So I've labeled these with some sort of a molecular tag that likes to be close to other like molecular tags. So there's an attraction here. So now we're talking about forces and interactions between molecules. So what happens if I label these so that they interact, and then I wait? What do you expect to happen?
Do they only attract themselves?
Yeah, they're only attracting. So like it would be as if the blue dye molecule were attracted to other blue dye molecules in that case.
Then I'd assume separation.
Right. OK. So if they're attracted to each other, and there's no other forces in this, let's see. You might expect, after waiting for some time, that now the molecules have clustered. OK, so in this case, interatomic or molecular. If these are atoms, I would talk about interatomic forces. If they're molecules, I'll say intermolecular forces. Same thermodynamics. Interatomic or molecular interactions cause spontaneous unmixing. All right, so we talked about mixing, and now it's unmixing. So this can happen too. And there'll be plenty of examples. Maybe you're already familiar with some. OK, and you can also, I won't draw this. So you could also consider the case of repulsive interactions. So let's say that those molecules, instead of attracting each other, were repelled from each other. Think about how you sit in a lecture room when it's an exam when we told you not to sit next to anybody. Do you become completely disordered or more ordered? More ordered. You become more ordered. Because if I have a person, I know that I only have to go 2 chairs over to find another person. And I go 2 chairs over to find another person. That's order. Right? So is that increase in entropy or decrease in entropy? That's a decrease in entropy. Right. So from this central frame to the right-hand frame, is that an increase in entropy or decrease in entropy? Decrease. It's a decrease in entropy. And the case of the students taking an exam and a lecture hall, that's also a decrease in entropy relative to, say, right now, where you look more disordered than that. There's some clusters, there's some lone people, right? It's sort of more disordered. OK. Yes, please.
So then with the balance in entropy, like you said, how everything always has to increase, would that come from doing work to label the molecules? How does it balance?
Not quite. But balance is the key thing. We're heading exactly towards this idea of balance. So thank you for saying balance. OK. So now everyone, let's see. So you got this idea of disorder and a basic notion of entropy. And now we've started to introduce the fact that molecules can interact with each other. And an interaction is typically characterized by an energy of any interaction. So there's energy involved. And I think these are concepts which you're already familiar with. So we're going to now review endothermic and exothermic reactions, right, in this context. So who's here heard of endothermic and exothermic? All right, everybody raised their hand, except for Akshay. All right, so now we get to play with the hot packs. But wait till I say you play with the hot packs. All right. So we're going to start with endothermic process. Endothermic process. Endothermic. Example. OK, so an example of an endothermic process is ammonium nitrate dissolving in water. So I'm going to draw it like this. N moles of ammonium nitrate plus m moles of water are going to react. And the reaction product is going to be a solution so even though this kind of just looks like you dissolved or you just mixed, you can still talk about it as a reaction. So this over here is pure solid. So this is what we call in thermodynamics a pure material. And it's in its standard state. Ammonium nitrate will sit in a jar. It's a solid at room temperature and atmospheric pressure. All right, and this over here is a pure liquid. OK. So this is a pure solid, and this is a pure liquid. And what's this on the right-hand side? It's a mixture. It's a liquid solution. In thermodynamics, and this is terminology, you have to get used to it, the word solution and the word mixture are basically interchangeable. Solution to us does not mean it's a liquid. Solutions could be liquid, gas, or solid. In fact, in this class, usually they're solid. So just get used to it. There's no way around it. So this is a liquid solution. In this case, it's a liquid solution. Or mixture, if you like. Liquid solution. OK, so I need to get more board space here. OK, so this process This process absorbs a finite amount of heat from the surroundings. It's an endothermic process. So it absorbs an energy, Q, this is in units of joules, it's an energy, from the surroundings. Sometimes this is called the heat of solution. Later on in this class, we'll show that this is related to the enthalpy of solution. We'll start using the word enthalpy, but for today's lecture, it's enough to think about heat and energy. OK, so in going from left to right, does the energy of the system increase or decrease? It increases because it's endothermic. It got energy from the surroundings, right? Does the entropy increase or decrease? It increases. And it's OK if you didn't have an intuition for that now. The reason it increased is because on the left hand, you had a solid phase. And then every n moles of that solid went into a liquid phase. And liquids tend to have much higher entropy than solids. They're more disordered, right? A solid is like everyone at every other chair. A liquid is somehow more disordered. So that was right. So in this case, the energy and entropy both increase. OK, so before we learned that nature likes to increase the entropy of the system. So that would seem to drive the reaction to the right. But if you've taken a physics class, you were probably told that nature likes to decrease the energy, which would drive the reaction to the left. Right? And both of those things are true in the right context. So what gives? All right, so we're going to find out what gives. OK, so open your, take your instant cold packs, which is the, not the one that says warm relief, the one that's blue. All right, so, OK, so this is a Dynarex instant cold pack. This is just a snapshot from the safety data sheet. Dynarex instant cold pack. If you're ever looking for your first choice for gloves, I guess it's the Tillotson Healthcare Corporation. All right, so this is the SDS, and this is telling you that it's made of ammonium nitrate pellets surrounded by a small rupturable plastic bag filled with water. So we're going to figure this out. Does this reaction stay on the left-hand side, or does it go spontaneously to the right-hand side? So what do you think? Everyone who thinks it's going to go to the right, shout. Or raise your hand. Yay, OK. So squeeze together here. So here we go. I'm going to squeeze together. OK. Ah. Cold. All right, so is it cold? Yeah. So is it spontaneously went to the right or the left? Where does it go? It goes to the right. So it's absorbing heat from your hands. All right, you feel cold. All right. So in this case, entropy, right? It spontaneously went to the right, which means entropy increased. But the energy also increased. So it's like we weren't sure what was going to happen. But in this case, entropy drives, I'm being really sloppy here, sorry. Entropy drives the reaction. It's the entropy consideration. Nature thinks about it, figures out the right balance, and say, entropy is going to win. We're going to make a solution. OK. So, OK, so now we're going to do the opposite case, which is exothermic. Exothermic process. That was satisfying, right? I like that. So exothermic process, for example, crystallization of sodium acetate. From a solution. So we started with a solution, and we're going to crystallize sodium acetate. So CH3COONA. Let's see, the way I wrote this was like this. X, H2O, Z. Let's see, reacts. The reaction is like this. It goes with some heat Q, and it becomes CH3COONA. Y. I'm going to put a little solid there because it came out of solution, formed a solid crystal. And then CH3COONA X minus Y H2O. Okay, so someone tell me, well, okay, so I told you this is a solution, right? This is a solution, it's a liquid solution of X moles of sodium acetate into Z moles of water. All right, what is, someone repeat for me, what is this material? What is this phase? Solid sodium acetate. All right, and what is this material over here, this phase? It's liquid. Is it a pure material? It's still a solution, right? So we have solutions on both sides, but they have different concentrations. We've conserved moles, right? We haven't created or destroyed matter. All right, so this is a liquid solution. But in the hot pack we're about to use, it's supersaturated. So ask me questions in a minute about what that means. We'll come back to that concept later in the class. It's a supersaturated liquid solution, so it's non-equilibrium. Then over here, we have a pure solid. And over here, we have a liquid solution. And what do you think would be the right term to characterize this liquid solution? A liquid solution in equilibrium with the solid solute is a saturated solution. Yeah, saturated. So if that didn't come to your tongue right away, that's fine. That's a concept which we're going to cover in detail, right, in a number of weeks from now. All right, so we start with a supersaturated solution and we get a saturated solution. Okay, so okay, so I told you this was exothermic, so I'm not going to ask you, what's the sign of Q. This process releases heat energy Q to the surroundings. So, all right. So would you say the energy of this system increases or decreases as it goes from left to right? Decreases. Exothermic. It lost energy. Okay. So energy. All right. What about the entropy of the system? Does it increase or decrease from left to right? Decreases, right? It decreases. You started with all the sodium acetate in a liquid state, and then you took some of it out and made it a solid. And I told you before that the solids tend to have lower entropy. So the entropy decreased. So energy and entropy they decrease. Both. Key is that they both decrease. Okay. All right. So nature likes to maximize entropy, but it also likes to minimize energy. So what's going to happen? Okay. So demo number 2. Right. So grab your instant hot pack. Let's see. There we go. So this is instant hot pack from Danyang Rapid and Aid Hot and Cold Therapy Products Company Limited, and it is made up of sodium acetate and water, right? That's what's in here. So I'll tell you what's actually. I'll show you a video of what this might look like in a minute, but let's test it. Let's do the experiment. Let's figure out if it goes left or right. So I did this the other day. It's like fold top to bottom to pop inner fluid bag and shake. Okay, so I'm folding the top to the bottom. Certain amount of strength required to be in this class. Ah, there we go. Okay. Oh, it's like it's hot. This is like a PE credit. I should get a PE credit for this. All right, who's got popping? I hear some popping sounds. It gets hot, right? Okay, so what's going on? Ah, yeah. Okay, so what happened? Some people are still struggling. It's actually really tricky. For those of you whose bags popped, can you tell me what happened? Somebody tell me what happened. It warmed up. It got hot. So did the reaction, where's equilibrium here? To the right or to the left? To the right. So it's weird, right? Entropy decreased. So in this case, unlike the previous case, so in the previous case, entropy seemed to win. Nature got to increase its entropy. But in this case, energy seems to win. Nature got to decrease its energy. So the balance was different. Let me show you a video of what these look like. All right. So we've seen two examples, and we've done two experiments. And we've seen that in one example, entropy seemed to rule the day, win the day. But in the other example, entropy or energy seemed to rule the day. I forget which one I said first. Right. So on the one hand, we have entropy or disorder. And on the other hand, we have energy, or what we will more commonly use in this class, which is enthalpy. They're not identically the same thing. So we'll cover enthalpy in plenty of detail in later lectures. But for today, we can use them interchangeably. So on the other hand, we have energy or enthalpy. And this question of balance is everything. So here's a Planck, and there's the fulcrum. And this is basically thermodynamics. Thermodynamics is nature's way of balancing entropy with enthalpy. And so what we're going to do is spend a semester learning how to calculate the balance for all sorts of different physical situations, mostly with solids, but also reacting chemicals, liquids, solid gas systems, and systems of interest, right, to modern material science. So what happens when we get the final answer? So OK, I'm going to move on. I have a couple slides to share now with to introduce you to the concept of phase diagrams, which is the way that we communicate with each other in material science, what the answer is, what's the balance. Before I move on, do we have any questions about these hot and cold packs, endothermic, exothermic processes? OK. So you might not know in advance the balance, right? One chemical system we just showed you, at room temperature and atmospheric pressure, preferred to maximize entropy. The other system, at the same set of conditions, preferred to minimize energy. So fortunately, there's a rigorous theoretical framework to calculate the balance, and that's what we're here to learn. Once you've calculated the balance for a given material, you want to communicate that answer to other people. And this is where phase diagrams come in. Phase diagrams are the tool, the visual tool by which, within material science, we communicate what that answer is, what nature will prefer at a given set of conditions. So I want to show you some examples of phase diagrams. If I have one deliverable in this class to you when you walk out of here in December, it's that you know how to use phase diagrams and you know where they come from. That's the core of thermodynamics and material science, unlike, let's say, mechanical engineering. Right? So this is the water phase diagram. Let's see, I assume that most people have seen the water phase diagram before. What's kind of cool about this water phase diagram is that it covers a very large range of pressure. So this is pressure on the y-axis, and the x-axis is temperature. And the colors here show you what the right balance is between enthalpy and entropy. So for example, at a given pressure, let's say atmospheric pressure, where is that? Here, right? When you heat up, you go from ice, which is a low entropy state, to water, which is a medium entropy state, to, I'm like down here, to vapor, which is a high entropy state. On the other hand, it turns out pressure goes the other direction. Pressure, we haven't talked about volume, but pressure, increasing pressure favors smaller material. That makes sense, right? So as you go from the vapor to this solid, and then these other phases of ice, which you might find in the core of distant planets, the volume per mole becomes smaller. Crystal structure becomes different. They're different materials. So this is kind of neat. You have like 11 phases of ice. I think there are 12 known now. They're labeled with these different Roman numerals. And so this is one thing that we get used to in thermodynamics, is that there are many different solid phases of a material. They're, in a sense, different phases. They're different materials. They behave differently. They have different structure, and therefore they have different properties. I was just speaking with one of my Europe advisees who she spent her summer at JPL testing the mechanical properties of drill bits on different phases of ice. Why? Because they're going to land a rover on Europa, and they want to drill through, they want to go ice fishing. They want to drill through the ice core of Europa to get to the liquid underneath. And they might expect different phases of ice than the normal terrestrial ice that we're familiar with, and it'll have different properties, and therefore it will wear the drill bit differently, and they have to know how it will wear the drill bit, right? You'd hate to fly all the way to Europa and have something like the drill bit failure ruin the mission. So it's kind of interesting. She just told me about this just before this class. So here's another example. Here's a binary phase diagram. Here, the y-axis is temperature, and what's the x-axis? I heard something like concentration, which is about right. It's composition. So this is a sort of complicated diagram which you're going to know by the back of your hand when you walk out of this class. So this is the copper-zinc system. This is called the liquidus line. Above this line, the system is a uniform liquid mixture. Below this line, there's a slew of solid phases. Alpha, beta, gamma, delta, epsilon, eta. Which phase or combination of phases, see this region I know is a mixture of alpha and beta, you'll learn that. How the system behaves depends on where you are in temperature, pressure, and composition. And that's something, this is an equilibrium phase diagram, well established because that's brass. It's an important metal, alloy. And we'll learn how to calculate these phase diagrams. There's a lot more. So the types of phase diagrams, that's a binary phase diagram, a classic eutectic. Phase diagrams don't have to be composition, temperature, and pressure. They can be electrical potential and pH. So a Porbet diagram, like you would use to predict corrosion or to optimize a battery, gives you the phase that you might expect as a function of aqueous solution pH and electrochemical potential or electrical potential relative to a standard electrode. Here's a ternary phase diagram. So here, instead of 2 elements or pure materials, we now have 3, titanium, tungsten, and carbon. So this is going to be all sorts of high-performance titanium, tungsten alloys in there. Here, there was no more room left on the page to do temperature and pressure, so those are in some sense in the 3rd and 4th dimensions, but they're there. And this is something that's near and dear to my heart because I work on a lot of oxide and sulfide electronic materials. This is a Richardson-Ellingham diagram, which isn't quite a phase diagram, but it does tell you whether nature predicts the metal or the metal oxide as a function of temperature and oxygen partial pressure. So this is very useful if you are, for example, making a transistor. You have to know how to control the oxidation process of silicon. Or if you're smelting, or any number of other sort of interesting processes that are important. So we're going to learn how nature finds this balance. And we're going to learn how to interpret these phase diagrams. But in practice, calculating one of these phase diagrams would take you a really long time, and you'd get a paper out of it, and you'd feel very accomplished. But what if you're out there in the world, and you have to make engineering decisions, and you have 7 minutes before your boss tells you, what percentage carbon do we want in this steel? All right? You don't go to the blackboard. You go to computerized tools. So the idea that you could calculate phase diagrams with a computer, that idea is called CalFed. It's kind of funny that that idea would have an acronym, but it does. It's called CalFed. And there are many CalFed software packages out there. What they do is they take materials data from databases, which often are proprietary, and they calculate the balance for a given temperature or pressure or composition or a pH or electric field or what have you, and they tell you the answer. So these are really indispensable once you leave here and you go off to your next position, whether it's in research or industry or what have you. And so we're going to spend a little bit of time in this class getting familiar with one of these, thermocalc. The reason why we're going to get familiar with thermocalc is because they have a free educational version, and it's relatively user-friendly. So you have to think a couple weeks until we're actually asking you to use thermocalc in your PSETs. But if you want to just download this on your computer, install it, get ahead of any problems, it tends to work well on both PCs and Macs, and play around a little bit. So this course, the thermodynamics section of this course basically has 3 parts. The first 7 lectures are introducing the concept of equilibrium. That is, this balance, right? How does nature determine the equilibrium situation, the most balanced situation for any given set of conditions? And then we're going to apply that concept. We apply the concept of equilibrium to increasingly complex physical systems to calculate these phase diagrams, to figure out where they come from, how to make them, how to read them, how to use them. And then at the very end of the course, we're going to come back to some foundational material. We're going to come all the way back to statistical physics for babies and do some slightly more sophisticated analyses of entropy and how it relates to, let's say, configurations of molecules. Do some foundational work. We might even mention Carnot cycles at the very end of class. OK. I already told you about the resources online, so I'll leave you with this. So Arnold Sommerfeld was one of the fathers of quantum mechanics. The point is that he was a smart person. No dummy when it comes to science. And this is a very famous quote. There's a website devoted to quotes about thermo, by the way. But this is the one that gets most often related, so I'll read it. He said, "Thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it, except for 1 or 2 small points. The third time you go through it, you know you don't understand it. But by that time, you're used to it, so it doesn't bother you anymore." Right? And this is consistent with most people's experience of learning thermo. This is a bit of a disclaimer, because this is the first time you go through it. So this is a tricky subject. And you shouldn't feel badly about yourself if you leave this course thinking that, I know how to use a phase diagram. OK, thermocalc, that's neat. But what just happened? All right, that's perfectly natural.